Welcome back. I want to show you one last example, and this is probably the best example of why dynamic programming is so important. And as you remember, when I say dynamic programming, which sounds kind of confusing, just think of caching, of optimizing something using a cache. One of the best examples of why dynamic programming is so good is our good old friend Fibonacci sequence. We learned about this in our recursion section of the course, where the previous two numbers add up to the next number. So that 13 is 5 plus 8, 34 is 13 plus 21, and it keeps growing, keeps growing, keeps growing. And we learn how to calculate that, right? We were able to calculate the Fibonacci number quite easily. We had function, Fibonacci, which is a really hard name to spell. I believe it's this way. And all we did was we said, using recursion, we had a base case of n is less than 2. In that case, we'll return n. Otherwise, we did some fun recursion. We return Fibonacci n minus 1 plus Fibonacci n minus 2. So that if I want to find the Fibonacci number at index of, let's say, 6, and I run this, and this should be n as a number. Let's run that again. I get 8 because 0, 1, 2, 3, 4, 5, 6 is 8. If I do 7, I should get 13. Awesome. This is something that we should be familiar with. But let me ask you a question. How efficient is this function? And we've talked about it before, right? It's not very efficient. If I have a variable here that says, let's call it calculations, which will equal to 0, and we're just going to increment this every time this function gets called. And because it's recursive, we know that it gets called a lot of times. If I do Fibonacci 7, how many calculations is that? That's 13 calculations. So 13 times that we ran through the Fibonacci function. What if I increase that to 8? 21. Okay, what about 9? 34. What about 10? 55. All right, it's increasing pretty fast. What if I do 12? 144 calculations just to get the 12th index. Wow. What if I do 15? 610 calculations. What about 20? Holy moly, over 6,000 calculations. And just for fun, what if I do 25? Oh boy. All right, one last time just because we're having fun. 30. All right, that's a lot of calculations. And by the way, if you want your browser to crash, just type in 50 or 60 and see what happens there. Regardless, if we look at this, is pretty terrible. Just to calculate the 30th number or index of a Fibonacci sequence takes that many steps, that many calculations. That is a lot. It's not very efficient. And we know this, right? Because in our recursion section, we talked about how that Fibonacci sequence and the way we're running the function is O of 2 to the power of n. Really, really bad time complexity. As we saw, just doing 30 calculations takes a lot of steps. And remember, with recursion, we're adding every nested function call adds to the stack, which increases our memory complexity. And we would never want to do an operation that costs this much in real life. So how can we make it more efficient? Can we make it more efficient? I mean, if you wrote that function, is your boss going to fire you because it scales so horribly? I mean, if your boss is horrible, maybe. But if you know dynamic programming, you can avoid this. Because what if I told you that we can do O of n with this function? Because with dynamic programming, we can. That's right. We can go from O of 2 to the power of n all the way down to O of n. Sounds like magic, doesn't it? And this is where we get to the next step of our dynamic programming. We can reduce the time and space complexity of our algorithm by using memoization. And we can do this because the solution to each subproblem is what we call optimal. That means we do a lot of problems repeatedly that are the same. In the next video, we're going to explain this concept and see how we can use memoization. I'll see you in that one. Bye-bye.